Hi everyone, welcome and welcome to the Friday's lecture. I hope you had a good long weekend. So let's get into the class. Hi everyone, welcome and welcome to the Friday's lecture. I hope you had a good long weekend. I'll silence that, sorry about that, bit of a feedback loop. My streaming video didn't have the volume turned off, it's now off. So we're good to go. Let's get into our slides. First of all, assignment 2, I've had a bunch of questions that about this, and I was talking to the tutors earlier today. It's incredibly important that you get your contribution statements right. So, in an ideal world, every member of the group contributes equally, and that's awesome if that happens. But in real life, often that doesn't happen, and we have an assessment scheme and a marking scheme which is designed for the real world, and it will scale people according to the contribution. And it's incredibly important for you, as a matter of fairness, that you fill those statements in correctly. So if someone has only been doing a small amount of work, whether because they've been ill or something like that, or just because they've not engaged, that needs to be reflected in the contribution statement. And if you're someone who's done more than your share of the work, it's very important that the contribution statement accurately reflects that. And importantly, if you're in a group and someone has been unable to contribute for a really good reason, like they're in hospital or something, this system deals with that, because that person should lower their contribution statement, the other people raise their contribution statements accordingly, and the person who was unable to contribute because they were ill or whatever just puts in a special consideration form, and they will be appropriately compensated through this special consideration system. Okay, so that hopefully that makes sense to you all. Now let me just see if there are any chats here, please. Any questions, please let me know. Any questions about that, please let me know. Also, academic integrity. It's incredibly important that you acknowledge outside sources. Some people have found like old assignments and stuff that have some code that's relevant. You're allowed to use that, but you have to acknowledge it, okay? And not only do you have to acknowledge it, you have to acknowledge it at each stage for each deliverable where that code is visible, okay? So if you add it in earlier in the assignment and say, oh, look, we took this code from such and such a place, that message in your originality statement needs to be there for every deliverable in which that code is still there. You can't just let it disappear it later on, okay? You need to continuously acknowledge the origin of that code, all right? So very, very important you do that. So if you found some code that you want to use and you put it in there, that's absolutely fine, but you need to acknowledge it. You also need to remember that if you use someone else's code and you acknowledge it, all's good, but you get marked on your original contribution. So if you have some core code that you got from somewhere else and you acknowledge that, you will not get an academic misconduct problem around that, but you will get reduced marks because that core part you didn't do yourself, okay? So obviously we want to assess you on what you've actually done. There are no labs in the upcoming weeks, please note that. Piazza is still going, and so forth. Someone says, do you have to put contribution statement for all the tasks? You just fill in the contribution statements that we give you in the admin folder. So, originality statement. Okay, so the contribution statement is something you sign off for each deliverable. It's in the admin folder. There's a file there you need to fill in with the contributions. And the originality statement is also something you fill in the admin folder. Okay, so just fill in those forms. So there's nothing new here. I'm not telling you anything you don't already know. I'm just reinforcing that you need to do this accurately and you need to do it properly. Okay, that's all. Any other questions on that? And I'll try and answer them. But hopefully that's fairly obvious. But some tutors came to me and said they were worried about this stuff, so they asked me to emphasize it. Okay. All right. Now let's get into the lecture. Today we're going to do A5. We started it in the last lecture, which was actually Monday 10 days ago. We started this, so I'm not going to go through this in detail because you've already seen these slides. If you haven't, go back and look at the video. But I am going to very quickly recap it to refresh your memory, okay? So we went through all these slides, we did the mini quiz, but we didn't write any code. Now we're going to write the code. Okay, so let's go through this. So abstract data types, we were looking at how to implement a set. We went and implemented the set using a hash map, right? Remember that? We did a hash map, okay? Then we said, okay, we can also implement it, instead of using a hash map, we can use a tree. And we talked about what a tree looks like, and we talked specifically about a binary search tree. A binary search tree is a tree with two nodes, at most two subnodes at each point in the tree, and each node may contain a key and a value, or just keys, and up to 2 children, okay? And the nodes are ordered. That's very important. They're ordered so you can search, okay? And so the left subtree contains only keys less than the key at that node, and the right subtree ones that are greater than. Okay, and I gave this example here. So there's the same set of fruit that we saw go into the hash table. They're now being put into a tree. I walked through very carefully how that tree got to be in that shape. Question I want people to try and answer on chat. What happens? How can the order in which you add the fruit affect this, and what's the worst consequence when we use a binary search tree? What's the worst consequence relating to the order in which we add the elements to the set? So I'm looking for people to answer that on the chat. Now I'm just going to step you through these animations. I did this before. We're adding different fruit here. You can see them all being added one by one by one, and you can see the tree being constructed in that shape. And then we can do a search. I think we're going to do a search in a second. Yeah, we're going to look for orange, and we have to look down the tree to find the orange. And we look to see the grape, and you see to find the grape we go to the apple, and it's not apple, and then we go to the right because G is greater than A, so we go to the right and we get to orange, and it's not orange, and so then we look to the left because G is less than O for orange. We get to the banana, and banana is not equal to grape, so then we look to the right of banana because G is greater than B. We get to the mango, it's not equal to mango, so then we look to the left of mango because G is less than M. And then we get to the cherry, and it's not the cherry, so then we look to the right of the cherry, and indeed we find a node where the value is grape, which is the one we're looking for, so we found it. And then we look for fig, same process, but in this case we get right down to the end there. We look to the grape, we look to the left of grape because F comes before G, and there's nothing there, okay? And that tells us that this tree does not contain fig. Is that alphabetical order? This particular search tree is doing stuff in alphabetical order. Yes, it is. And I explained all that in the last lecture, and you can see here, and I just walked through examples here where I pointed out how we navigated the tree according to alphabetical order. But the search tree isn't necessarily alphabetical, of course, because we're doing generics. Okay, so it could be any type. So it's some notion of ordering. These could be vehicles. They could be student IDs. So whatever you put in here, you've got to have some notion of ordering, which is an interesting question. How do you order things in general? If we don't even know the type, then that might be hard. Java has a way of dealing with that, and it can that's whether it implements the comparable interface or the compares to interface, and we can use that. But a more general way of doing it is just to use what can we use that every object in Java has. There's something that every object in Java has that we can use for comparison. Anyone? What can we do in Java? Every object has something that we can use as the basis for comparison. Can anyone suggest what that might be? It's got a hash code. It's actually got a hash code, okay? ASCII codes only apply to strings, okay? But hash codes is something that everything has, okay? Every object has a hash code. So we can use a hash code for all objects, and that allows us to make trees using any kind of object. It doesn't have to be a string, it can be anything. We can just say, is the hash higher, greater than, less than? In the example I've drawn for you on PowerPoint, I've used alphabetical ordering just for illustration purposes because it makes it easy to understand. But if we use hash codes, we don't know what the hash codes of those strings are. It could be kind of anything, so the ordering would be kind of hard to figure out. And I'd have to make the diagram a lot more complicated to explain that. But we can use whatever we want to do the searching as long as it's deterministic. And I explained determinism to you before. It has to be deterministic. So each time you look, you know whether to go to the left or the right at that point. And it can be done alphabetically, like in this visual example on PowerPoint, or it can be done using a hash code, which is actually what we're going to do when we write the code. Okay, and then you can remove elements from a tree and so forth. And I point out here that when we try and remove something, this is actually an interesting problem. Okay, so we're going to get up to removing elements later in the class when we write the code, because we have to do that's an element, that's something we have to do with the set operation. One of the things we can do is remove something from the set. Okay, and so let's just go back here, and so if we remove the grape, it's kind of trivial, right? We say, okay, let's remove the grape, and then we leave that node pointing to nothing, okay, and the grape's gone. All right, but if we remove the pear, the problem's more interesting, right? We remove that pear, and what happens? Okay, we've got this nothing thing there, okay? Then if I want to look for peach or plum, there's a little bit of a problem because I don't know whether to go left or right because I don't know if it need to go whether it need to go left or right because there's no value in that node now. It's gone. Okay, so we've broken the tree. Okay, we didn't break the tree when we removed grape because that was a leaf on the tree and it makes no difference. Nothing has to go left or right. But we did break the tree really badly when we did this because now peach and plum, there's no way to find out whether you go to them because you don't know what they're greater than or less than to. So we need a way to solve that. And what we do is, in fact, one way to do it is to say, let's take everything below that point. So the peach and the plum in this example, take everything below that point and put them back in the tree. So start over again. So we do this, add the peach in, and that's where it comes to, and then we add the plum. Okay, so one way to solve this problem, there's multiple ways to solve it. One way to solve the problem is to just take everything below the point where the tree got disconnected, so it got disconnected here, and just chop all this stuff off and pop it back into the tree and let it go to its natural place. And that's what this illustration is doing for you. Okay, so we take all those things and pop them back into the tree and let them go to their natural place. All right, so that's one way of dealing with removal. Now we're ready to start writing code, so let's jump into the code. If you have any questions about trees, please pipe up. I want to emphasize, there's a point I really want to emphasize for everyone, and if you know people who aren't at the lecture, you might want to point this out to them. The lectures we're doing now are some of the most important lectures in the whole course. Why are they so important? Well, at the moment, this A series, the A1 through, I think 6 or 7, these lectures are so important because they're combining a lot of the really core elements of the class all together, okay? And we've done lists. We did 2 different kinds of lists. Now we're doing the second of 2 different kinds of sets. And then finally, we're going to do 2 different kinds of map, okay? And what's so interesting about these is they're reinforcing how data structures work, lists, sets, and maps. They're reinforcing that there are different ways of implementing these which make different trade-offs because you get to see the difference between an array list and a linked list. You get to see the difference between a hash set and a tree set, and likewise for the map. And importantly, they illustrate lots of concepts that you've been learning throughout the semester. They do things like recursion. They use all kinds of things. Okay, so if you're trying to revise things for the end of year exam, I strongly recommend that you make sure that you're on top of the stuff we're covering right now in class. Okay, and if you know people who aren't following the lectures, you should say to them, hey, you really want to go through these A lectures because that's the heart of the course. Okay, so now let's go and make ourselves a package, A5. And if you remember rightly, A4 was our implementation of the hash set. Okay, we had a set interface, we had a test we wrote for sets, and we have an empty tree set which we created in the last lecture. So now let's just copy all that code over like this and drop it into 5 like that. So we've just duplicated the code. Okay, we're adding them all to Git, and we're getting rid of this. And now let's see that there's our set interface, which we're implementing. Very, very simple. It's a simpler version than what Java has. Okay, there's our hash set, which we did last lecture. We're not looking at that now. Okay, and then we've got the test. Here's our tests. And our tree set, which is just at the moment empty. There's nothing in here. We haven't written this code yet. Okay, and so what we're going to do now is change this test so it tests the tree set at the moment. So we just set this to false. We wrote this boolean at the top so our test could test either the hash set or the tree set. You see that boolean gets checked there, and we either create a new hash set or a tree set. All right, so we've just changed that to false. Now we should run this test and find that everything fails, okay, because it's testing our tree code, which is unimplemented at this point. All right, so let's have a look. We should expect to see everything fail. All right, now previously everything worked because we were testing the hash set, which we'd fully implemented. Now we're testing the tree set, and you can see there's nothing there and nothing works. All right, that shouldn't be a surprise. Okay, there's the empty tree set class, right? This is the set. Now, what are we going to put in here? For the hash table, we put in, for the hash set, we put in a hash table. In here, we're going to put in a what? We're going to put in a binary search tree. Someone asks on the chat, is the tree set our implementation of a tree? Not quite. The tree set is our implementation of a tree set. Okay, that is a set that uses a tree. And so you can see here on the code, it says it's a set. Is the interface we're implementing, and we're going to do it by using a tree, just like previously we implemented a set using a hash table. Okay, and in here we wrote all this stuff about hash tables, and in this one we're going to write things that use a tree. Okay, and you saw the PowerPoint illustration. We implemented a set using a tree, and we're going to write that code here right now. And what we're going to have is an inner class here, which is going to be our tree. What kind of tree? A binary search tree. Okay, so our set is going to be implemented in terms of BST, BSTree, binary search tree, and we'll call it the tree, right? And we haven't written this class yet, so that's why it's red. And then we're going to have, was one other thing we need, apart from the tree, which we're going to store all the stuff, and there's something we need in here as well, which we also had in the hash table. Can anyone remember what that is? Something important for our set. We have a count of how many elements there are. It's kind of useful to have that. We can go through the tree and count everything up each time someone asks, but it's easy. A hash table is not a hash map, absolutely not. In the next lecture, we're going to go and implement a hash map. A hash map is a map, right? It's a map that gets implemented using a hash table. And in this code here, we had a set. This is a set that's implemented using a hash table, okay? This thing here is the hash table. That's our table. That's our hash table right there. Okay, that's a hash table, okay? But this is a set that is implemented using a hash table, okay? And now we're implementing a set using a tree, okay? So someone says, when you say we're implementing a set with a tree, are we just following the rules of tree? No, we're actually implementing it with a tree. We're going to build a tree, okay? We're going to have a tree inside of here, just like in this diagram, folks. Okay, let's go back here. That is a tree, okay? And think of this whole slide as being your set implementation, the fruit thing, okay? So we add something to fruit. We add apple to fruit. We add orange to fruit, and so forth, okay? So fruit, if you like, this thing here is the set. It's obviously, in this case, implemented using a tree, okay? This thing here is a tree. It lives inside the set. This is a set that is implemented using a tree. Previously, we had a set that was implemented using a hash table, okay? So this is what we're doing now is a set that's implemented using a tree. Okay, so this set, this one here, is a tree set, and it uses a tree, so we're going to have to make ourselves a tree, okay? So we're going to create a tree data structure, and this code here will be relatively simple, but it will use a tree data structure, which we haven't written yet. All right, so we need to count the number of elements. Elements, there it is. And so what we're going to do here is going to have a new inner class here, class BSTree. Okay, now we haven't implemented it yet, but what we're going to do is we're going to write an add method that uses the BSTree, so it's going to add something to the tree. We're going to write a remove method that removes something from this tree. We're going to have a contains method that checks this tree to see if something's in the tree. And we're going to have a size, and the size is actually really simple. We can write this right now. That's just going to return the number of elements, okay? So that's really simple. We could go and count all the stuff in the tree if we want, but that'd be a silly way to do it. It's better to just return the number of elements. Okay, and we're also going to have to put a toString method in here. Okay, the toString method, we can write that right now. At override, the toString method for this set is simply going to say, hey, tree, print out the print yourself out. Okay, so we're going to say public string toString. When I say print it out, I mean create a string that represents yourself. Okay, so toString, and then we say if the tree is null, if our tree is null, which means we don't have a set, it's an empty set, right? Okay, if it's an empty set, then we want to return an empty string probably, right? So we return empty string, okay? Otherwise, we just say to the tree, hey, tree, print, give us a string representation. So we just say else tree.toString return tree.toString. Okay. Now, at this stage, we haven't actually written our tree. Our tree's empty, right? We haven't written this class. This is the interesting part of this problem, is writing that thing. Okay, but this stuff here is our set. Okay, and our set's going to have an add method, a remove method, a contains method. Okay, we've just written the size method, which is very, very simple. It just returns this elements thing here, and we've got to make sure the count for that is correct. Every time we add something new, we increment it, and every time we remove something, we decrement it. Okay, and then when someone asks the size, we just return that value. Okay, I'll repeat again. We could figure out the number of elements just by walking through the tree and seeing how many nodes there are, but it's simpler just to keep track of it with a separate variable called elements. All right, now let me suggest that we go and write this code here. This is part of our set, and say how do we add something to our tree, right? We want to add something to our set. The way we add something to our set is by adding to the tree that lives inside of our set, okay? And so the way we do that first is we just do something like this. We'd say something like tree dot add. There's no add method yet, but pretend there is. Add element, okay? Now we need to know if when we added the thing to the tree, whether it was already there or not. So we're going to get our tree to return something, and if it returns null, if it doesn't return null, then we'll assume that we'll know that we successfully added it. Whereas if we tried to add something to the tree and the tree returned null, that's the tree telling us that the thing was already there. Okay, because remember with the set we don't do anything if the thing's already there. Okay, so we add this, and then what we're going to do is we're just going to increment the elements if we successfully added it, right? Like that. Okay, so that's all we need to do, assuming we've got an add method up here. So here what we're going to do is we're going to have a bs tree add t element like that. And we haven't written this yet, and we'll just return null. Okay, so our tree, this is our tree class here, a little inner class here, which is tree. At the moment, it's got one method, which is add, and at the moment, it's not good. It just returns null, so it's a very bad implementation. But you can see now that this would work if only the add method was correct. There's one thing I've forgotten here. Can anyone see what I've forgotten in this bit of code? There's something I should have done, which I haven't done yet, which is quite important. Right? Can anyone see what I've forgotten to do in this bit of code? There's something conspicuously missing. I forgot to check whether we actually have a tree yet, right? So I need to say this: if tree equals null, then make us a tree first. Okay, so we need to yeah, and if the tree is empty, it will also return null. So we also don't increment the elements. Okay, so let's just say here, if the tree is null, it means there is no tree, and then in that case we say create a tree. So we say tree equals new bs tree, like that. Okay, so now we have an empty tree. Okay, so if someone says add something and we don't have a tree at all, then we create an empty tree and then we start adding element. We try and add our element to it. Okay, and now when we add the element to it, we discover it returns null. It means, oh, that thing was already there, so nothing happened. Okay, in which case we don't increment elements. On the other hand, if it did return something non-null, then that means we did successfully add it, which means it's new, which means you need to increment the number of elements. Okay, so now that's very straightforward. And what we really need to do now is, actually let's do contains as well. Remove is going to be a bit more interesting, but we can write the contains method here as well. Again, I'm writing code, folks. Notice what I'm doing here. I'm assuming we've somehow or other done a beautiful job of implementing this, okay? But at the moment, it's not implemented at all, okay? I'm writing our set on the assumption that we've got a nice tree up here that works beautifully, okay? So we're suspending disbelief, which is often what you need to do when you write code. You assume that part of the thing that you need to do is already done, write that code, and then you fill in the parts that are missing, okay? So and if we want to see if the tree contains something, well, naturally what we're going to do is say, hey, tree, do you contain this element, okay? And but before we do that, we need to see if the tree itself is null. If there's no tree, then clearly this set does not contain the element. So the first thing we'll say is if tree equals null, then there's no tree. There's no tree, then therefore we've got an empty set and we don't have that element. So it would return false, right? So we can't possibly contain the element if there's no tree at all. Okay. Otherwise, what we're going to do is we're going to say else. We're going to write ourselves a find method. The find method is not a contains method. It's going to be more interesting than that. And we're going to write that in a minute. But let's just write this. We're going to say let's write ourselves up here in the tree. We're going to say bs tree find t element. And at the moment, again, we're going to have this essentially empty. Here we can write here fix me. Fix me. We've got to fix that up in a minute. And the same here. Okay, And so we've got an add method and a find method. And down here, we're going to say, okay, if our tree is null, then clearly it doesn't contain this element. Otherwise, we're going to say return else if, sorry, we'll look in the tree. We'll say if, actually, we can do this. We can say return tree dot find element. Now, it's either going to return null, which means it's not there, or something else, which means it is there. And so we're just going to say is not equal to null. Okay, so this thing here is a Boolean expression which will return true if this returned non-null. It'll return false if that returned null. It's going to return null when there's nothing, when the element doesn't exist in the tree, which is what we want. Okay, and it returns true if it returns non-null if the element was found. And then this thing here would equate to true. This is because it says if it's not null, then return then that would be true, and it would return true. Okay. So now what we've done is we've written add, we've written contains. We haven't done remove yet. We'll come to that last. We've written add and we've written contains, and we've written it all in terms of this hypothetical tree data structure here, which doesn't yet exist. Okay. So now let's go and write the tree data structure. Hopefully everyone can understand that. We've got a toString method, which also calls a method on the tree, which doesn't yet exist, a toString method, and we've got the contains and we've got the add. All right, so let's now fill in this tree. Okay, let's go back to the PowerPoint for a second. Look at what a tree looks like. A tree's like that. Okay, so we can think, what's really interesting to think about here, notice that if you were to get rid of this part of the thing, this stuff here is also a tree, and this stuff here is also a tree. And this stuff here is also a tree. We call this a recursive data type. Okay, recursive data type, because a tree consists of trees. Okay, and at each point we can have 2 subtrees, 1 subtree, or no subtrees. Okay, so we can have a left tree, a right tree, or just one or the other, just a left tree there, just a right tree here, or neither left nor right. Okay, and so each node in this example here is going to have how many values? It's going to have a left tree value, a right tree value, and its actual value, right? The key here. Okay, so that's what we're going to have in here. So let's write code for that. So our class is a tree, and the tree is a recursive data structure. So a tree contains trees, or may contain trees. And the way we're going to do that is we're going to say bs tree left and right. Okay, now they could be both be null. And the other thing it contains is the element, right? Which is going to be of type T. Oops, T, and we'll call that, what are we going to call that element? Okay, like that. All right, so we've got ourselves those things, which you can see, again, this one more time, you can see it here. So that's the left, that's the right, and that's the element. Okay, so left, right, and element, that's in our tree. Okay, and remember, we're writing a set here. Our set contains this tree which we're in the middle of creating. Okay, and when we do an add, we're going to add something to the tree. When we do a contains, we're going to find something in the tree. And when we do a toString, we're going to go to the tree's toString method. Okay, so this tree thing here is really, really important. Okay, let's get through and write this. Let's first of all do the add. Okay, so first of all, we need to add an element to the tree. Now, one thing that some of you, if you're really thinking hard and thinking ahead, one thing you might have remembered from the hash table is that we're allowed to add nulls to sets. Java actually allows you to add a null to a set. That's a complicating factor, and in fact, we're going to leave that till later. Okay, so let's just for the moment ignore the fact that you can add nulls. Okay, so if you're worried about that, let's just put that aside for the minute. Okay, and if you are interested and you're following what I'm doing, you may want to think ahead and think, how on earth are we going to deal with nulls? Okay, because Java allows you to add a null to a set, and we even have special code here, right? We've got test code here, which tests to make sure that we handle them properly. Okay, now let's get on and write our tree set. We're going to do an add, and so what are the possibilities here? First of all, there's a possibility we need to only add something to the right place. Okay, so we have to navigate. Remember on the PowerPoint animation when we went and added something? Let's go back here. Add. We're going to add the cherry, right? We add cherry. Watch how it happens. We've got to navigate our way to the right point in the tree. Then we add it. Okay. Yeah, Darren says on the chat that nulls can be used for leaves, and we see that in the example before, where sometimes the tree could naturally have nulls in it, and I gave an example. So it's possible that you end up with a tree with nulls in it. Therefore, we need to differentiate when the user has said, please add a null to my set, and from nulls that are living in the tree just by an artifact of the way we build our trees. So we need a way to deal with that. Don't worry about it too much. If you find that a bit head twisty, we're going to deal with it in a fairly simple way later. For now, we're just going to ignore the fact that Java allows you to add nulls. Okay, that's a very strange twist that Java has that allows you to add nulls. It's a very strange idea, slightly annoying idea. All right, so now remember what we just saw there. We've got to navigate our way to the right place to add this thing. That's the way trees work. So it's going to be recursive. The add method's going to be recursive. Again, to go back to this thing. When we added that grape and the cherry, we added it to this, and that said, hey, you got to add it over here. And this said, hey, you need to add it over here. And that said, and so forth. And eventually we got to the point where there's nothing there, and we got to create our tree and have the grape as the element. Okay, so now let's go here, and we're going to say if the tree that we're at has no element, then we're at the place where we can add something. This dot element equals null. Notice I'm saying this dot element because I'm talking about the element at this node of the tree, not the one that just got passed to us by the user. Okay, that's the one that gets passed by the user. This is a different element. This is the one that's at the tree node. Okay, that's an argument there. This is the actual field of the node. Okay, so if we've come to a point in the tree where we've got nothing there, then that's when we can place it. Okay. So we can say this dot element equals element, and then we can return ourselves. Okay, so we're returning the subtree that we are. Okay, that's an interesting thing we're going to do. We're going to return the subtree that we are, and notice that we need to return null if we couldn't add the element. In this case, we could add the element, so we're returning ourselves. Now, what's the other possibility? There are 4 possibilities here. We get to a node, it has no element. That's great. That's a place we can add our element. We get to a node, and it has an element, and it's not the one we want. And it could be on the left, and it could be on the right. That's 2 more cases. So that's 3 cases in total. There's a 4th case. What's the obvious 4th case? The 4th case is we get to a node, and the element of that node is actually the one that we're trying to add. If we're trying to add the same thing that's there, then we know that we don't add it because it means that we would have a duplicate in our set. So we want to check for that possibility as well. So we come to a node, we look at the element, and that element is what we're actually trying to add. In which case we just return null. Okay. So and remember, we have to use object equality here correctly because so that it actually makes sure that, for example, if you add the string cat or apple and apple, they could be different objects with the words apple in there. We need to use Java's object.equals to see if they're actually the same values. That is, they're both apples. They're both apples. Okay. So we're going to say here else if this dot element dot equals element. It means with this thing's already in the tree. The element you're trying to add is already in the tree. Then we return null. Right? Means already there. Okay, already in tree. Okay, so we return null, and then otherwise there's 2 cases, right? The left or the right. The left or the right. Okay, so we've considered the case where there's nothing, and that's where we add our element. Otherwise, we've considered the case where we've actually reached the one we're looking for, which means we return null. And then the next 2 cases are we need to go to the left or we need to go to the right. How do we do that? We compare the hash code of what we're trying to add with what's in the tree at this point, and then we go either left or right accordingly. Okay, and it doesn't actually matter which way we go as long as we're consistent and deterministic in our search. Okay, so you can write the tree either way to go greater than is left or greater than is right. It doesn't matter. Okay, so now we're going to say else if this this dot element dot hash code is less than or equal to element dot hash code, then in that case you're going to go to the right. Okay, why don't we return this if it's already in the tree? Because we want to be able to we want to find the case. Now I assume someone said they can't hear my voice, but I think that's just an issue with your you're streaming. All right. If no one can hear me, then you better yell on the chat. Why do we return null? Because we need to be able to know if we found null. One way to do it is we return that and then we check to see if the thing that got returned has the element we want. It's simpler just to do this. Okay. All right. So now what we can do is we can just say the following. Okay. So we're going to go if the thing that we're adding, the element, is greater than, we're going to go to the right. Okay. So we're going to say return right dot add element. Okay. So at this point, the thing we're trying to add is greater than. Let's just reverse the sense of this equation, make it a little bit more obvious. Oops, keys. Okay, there we go, like that. If the thing we're trying to add is greater than, if its hash code is greater than the hash code of the thing that's already there, then we'll add it to the right subtree. We'll add it to the right subtree. Okay. Now there's something wrong with what I've written here. What have I done wrong here? Okay. I'm gonna keep going. I'm gonna leave that bug in there. There's a clear bug in what I've just written. I want you to think about that, and I'm gonna keep going. I'm gonna wait for someone to say on the chat what I've done wrong, and I'm gonna go on the other case. So if it's greater than, we're gonna add to the right. Otherwise, what do? It must be on the other side. Okay. Else return left dot add element. Okay, and someone asked why do we have greater than or equal to? It doesn't matter which way we do it. We can do it either this way or that way, as long as we're consistent. Okay, we've covered all the cases, so we can get rid of that line of code. Okay, so let's look at this. Let's go through this again. We're trying to add it to this subtree. Remember, this is recursive, so it may not be the top tree. It could be a tree within the tree. Okay, so we're trying to add it here, and we look at the element. And we say if the element's null, then we're in the right place. We can just add it. Okay. Otherwise, if this element equals the element, then we've actually found what we want. So we return null, say, hey, we don't want to add this, okay? Because we've already found it. Otherwise, we look on, we check to see if the hash code of the thing we're trying to add is greater than. If it is, we go to the right and say, add it to that right subtree, okay? And if it's on the left, we add it to the, otherwise we add it to the left subtree. But there's still a problem with this code, and I'm waiting for someone to tell me what the problem is. I'm waiting for someone to tell me what the problem is here. There's something really obviously wrong here. Okay, I didn't check, guys. You should all be. You should see this straight away. I forgot to check. Yeah, great. Someone's already said it on the chat. Yeah, okay. So we need to check to see if it's actually null, right? Because if there is no right subtree, we need to create a right subtree. Yes, well done. So we say if right equals null, it means there is no right subtree. We need to create one before we go on and add it. Okay, so we say right equals new BS tree, like that. Okay, and then we need to do the same thing down here. Okay. If left equals null, then create that left one and then we add it. Okay, great. So now we have an add method. Let's just repeat what it does. We add the element. It first checks to see if the element at the tree where we're at is null, in which case if it is, we're ready to add it. Okay, then what we do is we say if it's equal, we ignore it because we've got nothing to do because it's already in the tree, and then we go to the if we go to the right subtree if the hash code being added, the hash code of the object being added is greater than the hash code of the object, the element. Otherwise, we go to the left. All right, and that way, and that need to check right and left are BS trees. Yeah, that's I think. That's what this is. I assume that there's just a lag in what I've written compared to what Brendan has asked. But if I've not answered Brendan's question, maybe he can rephrase it because I think he's just asking about this, which I now have. Okay. There's a lag with the streaming. All right. So we've done this. This should work now, but we have to write the toString method. Okay, before we can test it. Let's see.